All right, so we were talking about ALUs. And I even showed, like, ALUs are far more general than what we're going to do. Our ALU is only going to do addition and subtraction. But we even looked at, like, this ALU that came with digital. It's not built in like a regular component, but it is a custom circuit that you can import into your circuits. And all it is a series of these operators, add, subtract, and, or, exclusive or, not, negation, and I don't even know what these are. It's hard to see. But a bunch of operations that, depending on the input string, would specify which of these, A, B, which of these is actually being mapped to the output. So it's pretty cool. It's a simple design. Now, of course, each of these has its own design inside, right? Add, subtract, and, or, like, you know, we know that these all kind of have their own configurations. But this is the general idea of the ALU. Our ALU is going to be simpler. Anyways, this is like digital's ALU if you import it. Again, it's not a component. Like, you can't go find it up here. Component. There's no ALU in here. You'd have to import it some other way. There, ALU. Hey, it worked this time. Okay, cool. And it has that symbol, which is a custom symbol that you can do in digital, which is pretty cool. Anyways, because otherwise, if you import some other arbitrary custom, well, it'll just be a box by default, but the ALU, they added a custom little symbol for it, which is nice. All right. Designing a sophisticated ALU is not difficult. It's basically just a series of the operations and then a multiplexer, right? That's it. Integrating one into our larger architecture is going to be a challenge because of the design that we're going to use. So we're going to be building a working computational system. It's going to be functionally complete. It's going to have everything, but it's going to be limited in some of its, there will be some limitations, none of which are like computational limitations, but some constraints. And these constraints will make it difficult with our current iteration to have this like general purpose ALU. So we're going to have a very specific, simple version of an ALU that can do add and subtract, okay? Even with the simple ALU though, our computer will be Turing complete. And for those of you that don't know what it means, that's just a fancy way of saying like it can run Doom, okay? It can do anything any other computer can do, although ours is going to be constrained by the fact that it's going to be 8-bit as opposed to 64-bit or something. Okay, one may have noticed that the ALU is effectively a function that takes input. Oh, this is just me talking about. I'll read through this because I did talk about it a little bit last time. Takes inputs to produce an output. However, one may also notice the function may have side effects, changing the system status flags. In your computer science courses, there's been a strong emphasis avoiding side effects and writing pure functions, which is, this seems to violate. Yeah, for better or worse, under the hood, the common model design architecture for computers are very stateful. These designs are very stateful. They are. So side effects are going to be a thing. But fortunately, we really don't we don't have to go far off of our layers of abstraction to be able to start pretending things can be more pure and not stateful. All right. The ITER simple as possible architecture. If you go into Google and you type simple as possible architecture, you will find here. You will find this. Okay? It is a computer architecture design that is designed to be as simple as possible. There are technically simpler ones depending on your definition of simple, but this is our simple as possible design. And it was created by Malvino and Brown, right? This is going to be what we're working towards. However, we're going to be working towards a slightly modified version, not very much modified, but a slightly modified version based on the work of Ben Eater. Ben Eater has this YouTube series where they build like this like computer that we're going to kind of be working as well. The thing we're working towards is not going to be an exact copy of like Ben Eater's version of the simplest possible design, but it's going to be close enough that we're going to call this the the either simple as possible architecture. All right? So at this stage, we've learned about all these components, and we started putting these components together into these like modules, like a RAM module, registers, this adder, right? All of these different things. Now we want to start putting them together in a coherent system. And we're going to want a bit of a roadmap to do that. We're not reinventing the wheel. We are going to be learning about how these computers work with a roadmap. And the roadmap is going to be this simple as possible, or either simple as possible design, or ESAP. Okay? Yeah. So this is the idea. All right? We've got this common bus. And all of these different components, all of these different modules are going to be connected to the bus so they can communicate with one another. But we saw with all those little signals, like we did with the RAM and the register, by controlling when we activate and deactivate certain modules, like output from this module and input to this module, we can move data around. We're just going to scale that idea up with additional modules. But what are we going to have on this system? Well, we're going to have a clock. That is the thing that synchronizes the whole computer. Everything that happens sequentially in the computer is going to be synchronized with the clock. There's going to be a lot of components within the computer that aren't sequential. They're just combinational circuits, like a basic adder. But nevertheless, there's going to be a general synchronization with everything going on in the system. And that's what the clock is. We also have RAM. But we also have this thing called a memory address register. Now, we know what a register is, but what's up with this memory address register? Well, we'll see that in a moment. Basically, the information on the bus is always changing. It's very transient, right? So if I want to, remember in our design how we had those separate signal lines for address? Right? Those two little signal lines, and we called that the address bus, and then we had the data bus. In our design, it's actually going to be a common bus. But if I want to specify a memory address, like memory address 2 from this data bus, and put it into RAM and tell, okay, output from memory address 2, well, we got a problem, because we're reading from the bus, memory address 2, and we're trying to output information to the bus. So a simple solution to that is create a register to isolate that from the bus, put the memory address in here, now we know the memory address, and now we can output to the bus. More on this in a moment, but that's the purpose of that. We've got this instruction register. This is going to be something we're working towards. This is one of the later things we're going to be talking about. But an instruction register is, well, our computer is going to, we want to be able to program our computer to say, like, add these two numbers together, for example. So I want to be able to put that instruction somewhere. That's what this is going to be. And this is the control signals that's going to be controlling when and every module is on and off and outputting and inputting and everything. This is something we're going to be working towards. This is one of the more complex aspects that we're building towards. Over here is the program counter. Very simple module. All it does is count with clock cycles sometimes. Basically, think of RAM. We store our programs in RAM and our data. But we want to start running our program. We probably start running our program at memory address. In our example, it's going to be starting at memory address 0. And then after we're done executing memory address 0, we need to go to the next memory address. So now it's 1, and then 2, and then 3, and so on. That keeps track of where we are in our program. Interestingly, it actually keeps track of the next instruction in RAM. But that's later. Register A, register B. We have two registers, A and B. These are just things that they're like our hands. We have RAM, and then we can put information in our hands that we're actively working with. We have our adder. Well, ALU, we're calling it the ALU, but it's really just the adder and subtractor, where based on the values in these registers, we can add them together. And we have an output register. This is going to be a way to display information. We're going to use 7-segment displays. Does anyone know what that is? You all know. If you don't know what it is, you do know what it is. That's these things. We're going to use these to output information. But what information do we want to output? Well, whatever we put into this output register. More on this later. Right now, I just kind of threw you into the deep end of this is our roadmap. And like, okay, well, that's a lot of information. Yeah, I know. It's our roadmap, and all we've really talked about so far is this, registers, and like our adder, okay? In fact, we already kind of had a design where we had RAM, a bus, and a single register. That's what you did on the test even, right? What would the signals be to move data around? So the design is simple to follow and understand while still being Turing complete. Further, it's a straightforward to add to. It scales really nicely. And it will also serve as the basis of going deeper in architecture complexity. So the ALU will serve as the starting point for our ESAP computer. We already kind of had some form of bus and whatnot, like I was saying, with the register and RAM. But we're going to revisit that. We're going to start with the ALU. And here's the design. Let's just open it here. Nope. There. Can you see that reasonably well? It's kind of hard to see. I think it'll be fine. So what do we have? Oh, okay, we've got our testing. We've got a clock, and the clock is hooked up to everything that's synchronous, which is, okay, the registers, sequential logic. The adder actually doesn't need a clock thing, just because it's always adding whatever the inputs are. So there's only really two things here that have the clock. You'll notice that the clock signal goes down. That's just for like visual clarity. It's just a clock signal. We have a bus. This is our data bus. Data 0 through 7, combined on one line. And down here we've got outputs, for no other reason of just observing the outputs. We have two registers, okay? The data can come in from the register. The clock goes to the register. That goes for A and B. And you'll notice that the registers have an input enable. Oh, no, input enable and output enable. We're using just a driver to turn output on or off. But remember, the drivers are great in that it can allow a signal or high impedance, right? Remember, that was important. And these signals are hooked up to some control lines here, AI, AO. A in, A out. Figure that makes good sense. B in, B out. And then here, we've got the adder. Now, what's neat about this design, I don't know if neat's the right word, but what I think is neat about this design is these registers, the output enable is here, but you'll notice that the signal going to the adder is before the driver. Meaning, remember how the registers are always outputting the data they're storing? Whatever Q is, it's always there. It's always outputting. So at any given time, the adder actually always has the sum of A and B. It always does, because A is always outputting its value. The driver blocks it from going this way, but the A can go into B, or sorry, into the adder. And then B, similarly, I mean, it could be this negated thing. And there. But with this design, the adder is always calculating the sum of the A register and the B register. However, we control whether, so this right here is always the sum, but we are using a driver to turn on and off when we really want to output from the ALU. Cool? I think that's pretty cool. And then finally, we've got the subtract line. We already saw it, right? We use the XOR as an inverter. And whenever sub is high, we also include 1 on the carry bit in for 2's complement. Pretty neat. Any questions about this general design here? There's a lot, but every single component we've explored before. And if you take your time, I know this can make perfect sense. We've got ways to put data in. register, register. This is always calculating the sum, but we may or may not want to actually output it to the data line, or like to the bus. And we've got our control signals here. So, for fun, what do we want to add together? Give me a number. 10. Perfect. So let's run. How do I put 10 into register A? Well, let's put 10 on there. So we put 10 on the data bus. Now, if I just run the clock, nothing's going to happen because I need to enable A in. Right? There. Now it should be in there. In fact, if we zoom in, did it get latch in there? Okay, whatever. So this value, yes, you can see, interestingly, this line here, which is from A, it's an A, which is 10. Now, why is it saying, here's an interesting thing. You might say, well, hold on. There's an A on this line, and that's coming from here. No, the A is from here. It can't go that way. Right? Now, what value do we want to put into B? 11. Pardon? 11. That's easy. Now, we don't want to A enable. We want B enable. Perfect. Okay, now I'm going to turn these off. Off as in putting them in the Z state, that high impedance state. Okay, let's turn B off. Okay, great. Now, everything's fine, everything's latched. I can spam the clock, nothing's going to happen because information has been latched in and A and B are not reading from the bus. So, what do we see here? Well, the data here is Z, the data here is Z, but the data out of A should be 10. And we could even see that A and B, it's really convenient that the values 10 and 11 label the registers that they're coming from. That's, to be clear, purely coincidental, just a fun little quirk. The fact that this is A is not because it's from the A register, but it's because the A register is storing the value 10, which in hex is 10. Similarly for B, it's kind of funny, right? So don't get it twisted there. It's not labeling itself, okay? Now, that means the value here should be 1,5 in hex, right? So what is 1,5 in hex? Well, that's 16 plus 5, 21. Is 10 plus 11, 21? Yep. If you're wondering how did I know? What? Because I hovered over here and it said OX, that tells me this is a hex number. I've got a 1 and a 5. If I have a 1 there, that means 16. And then a 5, that just means 5. So 16 plus 5 is 21, right? Cool. All right, so now, what do I want to do? Well, okay, we clearly see that A and B are 10 and 11 respectively. But for the fun of it, let's just go down here and do A out. We see 10, right? Notice we didn't need a clock pulse for the output to go there. No, the clock pulse only mattered when latching the data in, not from when outputting from a register. This is good in the sense that, like, I want to make sure the data from wherever it's coming from is ready to be latched in on the next clock pulse, right? And then, okay, if that's there, B out, we see 11. Cool. Should I do A out and B out at the same time? No. Everyone, no. Yeah, that will crash this. This is bad. We don't want to do that. So we'll turn that off. But let's output the ALU. What do we see? Well, that's 16 plus 4 plus 1, which is, of course, 21. And if we follow that trick of hex, we look at 4 bits at a time. 0001, that's a 1. 0101, that's a 5. 1, 5, hex. There we go. Cool. Now, for the fun of it, let's turn on sub. Whoa, we see everything turn on. Does that make sense? Well, 10 minus 11 is -1. What's -1 in 2's complement? All ones. Even if we weren't thinking in 2's complement, and we were thinking, no, this is unsigned. This is unsigned. Like, well, remember, in the way binary works, right? If I have, like, imagine I'm counting in binary. Let's just do 4 bits for fun, right? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Eventually, I get to like 1, 1, 1, 0, 1, 1, 1, 1. What comes after 1, 1, 1, 1? Let me lower this for you. What comes after 1, 1, 1, 1? 1, 0, 0, 0, 0, but of course that doesn't exist, so, you know. So if I'm at 0, 0, 0, 1, what comes before 0, 0, 0, 0, 0, 0, 0, 1? 0, 0, 0, 0. What comes before 0, 0, 0, 0? 1, 1, 1, 1. So like, it's still like an overflow issue, but backwards, right? Because the overflow goes in one way, but it also goes the other way. Also conveniently, you know, 2's complement is 2's complement. Cool? Cool. Cool. So we did the subtraction, and we suddenly get -1, which makes perfect sense. Cool, right? I think that's pretty cool. So great. Any questions about that? How about this? Let's do the sum. What if, let's see if we can get this working. Stop. Okay, so I'm going to put 1 into, nope, B. Okay? Perfect. And then I'm going to put nothing on the bus. All right? But I'm going to output the sum. What is A plus B right now? Well, A is 0 because I restarted it, right? And, you know, it's going to be nice and set it at 0. Let's make sure that's actually true. Let's A out, nothing there. B out should be 1. Perfect. We've got 0 and 1. What's A plus B? It's not a trick question. 1. Thank you. So let's output the ALU, but we're going to input it back into A. Okay? So the ALU, and I'm just going to spam. Watch what's going to happen. What am I doing? I'm just incrementing, yeah. I'm saying, you remember doing this on your calculators, being like, hey, I'm counting, right? Plus 1 equals, 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 right? That's all we're doing. Okay, I got 0 here, 1 here. Output the sum, but put it back into A, which immediately always gets fed back into the ALU, and we just output it, output it, output it, output it, output it. Pretty cool. I mean, we could play the same game and make it count by whatever we want. Here I'm having it count by ones, but you know, we can count by 2s, we can count by whatever we want, right? Pretty neat. All right? Let's keep going. Oh, we're getting there. Oh, halfway there, right? How do I know I'm halfway there? Because 1 more bit doubles the number. So let's press clock 100 and 20. Thank you. Oh, we're going to do this. You're here with me for the ride. I'm committed. And what should happen once we get to... All right, we're 3/4 of the way there. Oh, we're getting there. My arm's starting to hurt, though. I'm missing it. Now what's going to happen? In fact, oh shoot, I can't modify it. Okay, I'm going to pulse it. What's going to happen? Ah, back to 0, right? But what would be coming out of here? The carry bit. There'd be a 1 there because we overflowed. I should have added a little output signal here just so we could observe it for the fun of it. Any questions about what we were doing there? Again, you could start to see, okay, in the previous example where we were moving data around, we were just shuffling data around between RAM and a register. Now, we move data around from the input into some registers and from the ALU to a register, fine. But now we're performing an operation. We're doing arithmetic. Sure, it's simple, but we're doing computation now. And we were doing the computation by just controlling these signals. Cool? Let's just go backwards, though. Anyways, cool. I think that's pretty neat. Whoop. Nope. All right. I think we covered everything here. So how does this compare to the ESAP system? Well, we've got the data bus here in orange. Orange. We've got the clock, red. Then we've got the register. Over here, the register is above and below into the ALU. I just put the registers together in the ALU. But that's what we've got. We're missing several chunks, but we're working our way there. But that's what we got. Okay. It's possible to see how the ALU fits into the whole ESAP architecture. With the ALU, several components of the whole system are present: register A, B, ALU, data bus, and the clock. Cool? Cool. Further, the ALU does include the start of the control bus for the system. Yeah, so the bus, yeah. Or the control bus being like this right here. Here, this doesn't show the control bus. Okay, the control bus is like how all those control signals, but it's pretty straightforward. Like, okay, RAM has an input-output. ALU has really only an output. Register has an input-output, input-output. Okay? The layout of register B and the ALU are swapped. ALU is below both registers in the digital design, but between the register and the overview, this is an irrelevant. There's no meaning to this, okay? Like, don't think like, oh, why did he do that? I did that just because I wanted the registers to be next to each other. Other than that, I'm trying really hard to be following this design. I actually spent a lot of time thinking about how to lay out the system. Originally, I was going to have all of this on that side. So like we'd have like the data bus, and then the control bus could have been over here, and then all the components over there. But that became really difficult to manage because it just got too tall, and it wasn't going to work. So we're going to follow this design pretty well. Okay, as long as he inputs it out, yeah. So where they are doesn't really matter as long as everything's connected correctly. There's one slight difference. Yes. So you'll notice here is a difference I did intentionally. This is an example of where I'm breaking from the ESAP design. not only the simplest possible design, but even the Ben Eater design where they do it this way. You'll notice that the A register can read and write to the bus, but the B register can only read from the bus. Okay? In our design, we're going to be able to read and write to register B. Okay? Now, you might think like, well, why would I not want to be able to write back to the bus? We already have RAM, and if you really need a position, like the registers are like a nice and easy place to move data around, but we can use other RAM addresses to do the same thing, right? Because if you even think back to the RAM design, it was just a series of registers stacked on top of each other. So we already have a bunch of registers. So one more register to input, output, whatever. Here, the B register in this design is really acting as not even its own register, but like the ALU. Where whatever, like, if I have some value in here, I would say add to it. And I would add to it by inputting into the B register. But I would have no need to like get information out of the B register. Not overly important. Having an understanding of what this is requires a little bit more knowledge. But at the end of the day, there is a difference. Our design, we can read and write to the B register because it was trivial for us to add it. Like if I'm building this physically, this requires additional components to be able to read and write. In digital, I just click the mouse twice, right? Like it's easy. So it doesn't really matter to me. And it doesn't add any extra complexity for us. And it gives us a little bit more flexibility in terms of like when it comes to programming the system. But once we get there, you'll see there's always these trade-offs. Executing arithmetic. We already did this, right? Load 15 into A, 4 into B. And here's me showing the table for like how I did that, right? Well, if I wanted to store the value, now, why am I showing D in hex? There's not enough room horizontally to have a column for each of the D bits. So this is a brevity thing, which is usually why people are using hex in these cases anyways, so you know. So I want to put F, that was 15, and 4. So I put 15 on the D, AN, clock pulse. Later, eventually, I don't even include the clock pulse, kind of like on the test, right? You just assume each row is a clock pulse. Put 4 into the B register, there, clock pulse. And then output, well, that should be Z, output from the ALU. Here, we don't even need a clock pulse, actually, because, again, there's no clock pulse to output. It just, if you put output high, it outputs. So that's why it's 0. But it doesn't really matter so much, whether that was a 0 or a clock pulse, whatever. Effectively, functionally, the same thing. But, you know, for correctness, it's a 0 here because it doesn't actually matter. And here's how you would see it, right? Put that there, put that the 4 into the B. I think I have a GIF here somewhere. Yeah, check this out. I spent so much on this. Y'all better appreciate it. Appreciate it. Clap, yes, clap. Everybody, thank you. Yes, I know. All right, there we go. Anyways, I realized this GIF, we just did this in digital, right? So this serves more for later when you're reviewing. So I want to make sure I'm not missing anything important here. There's no need for a final clock pulse to output from the ALU, right? To provide another example, consider the problem of 15 minus 4. What would I need to do? Well, these are the steps, right? This is like the pseudocode. Load 15 into A, 4 into B, set the subtraction control signal, output from the ALU, store the result into the register A, output from register A. Right? I didn't need to store it back into register A, but whatever, I am. Okay? Just so it's saved somewhere. Because otherwise, the value on the ALU disappears until as soon as register A changes. Right? Some of these things can happen at the same time. Like 3 and 4 can happen at the same time. don't think that each instruction is necessary, like each step is necessarily one clock cycle. These two things can happen on the same clock cycle. We're doing subtraction and then output, right? That happens at the same time. After executing, yeah, there we go. And here's one warning because I got tripped up on this too. Be mindful of the current state of the system. Consider what happens when outputting the difference from the ALU to register A before and after the clock pulse. So what am I doing? 15 minus 4, that should be 11, right? And so that's 10, 11, okay? But then I do a clock pulse and store something into register A, and the control signals are set the same, and suddenly we see the value, like I just calculated 15 minus 4, and I stored it into A. Clock pulse, and suddenly the ALU is now saying like, no, you've got 7. The reason I have 7 is because the ALU is still outputting. The value 14 was saved into A. So it's like we did minus 4, but I didn't care. Like if I don't care about that second minus 4, well then I just stop outputting from the ALU. So you could be like, whoa, we just did it twice? What happened? No, we didn't. It's just by virtue of I put 11 into here, and then immediately the ALU is like, oh, well, 11 minus 4 is 7. So we're seeing it do it twice, even though we didn't really want it. But at the end of the day, the value we actually cared about is still safely stored in register A in this example. Okay. Any questions about any of that? Any questions, thoughts, concerns, comments, anything? All right, let's do an activity. Following how this table is created, okay? So use this general design of the table. I'm going to write down store result of 9 minus 3 in A. I don't mean just store 6 in A. I mean put 9 into A, 3 into B, perform the calculation, and store it back into A. That's what I want you to do. And you have to have it handed in by 11:20. If the question is unclear, ask.